Okay, Snell's law is symmetric. So whenever you go from a medium of low refractive index into a medium of high refractive index, it bends in. So light comes in like this, high refractive index, it bends out like that, lower angle. By symmetry, if it goes the other way, it has to bend out. So if you end up having light coming in like this at an angle, it has to bend sharper on this side. So not as big an angle here, sharp angle on that side. However, if you keep doing that, you eventually run out of angle on this side. The biggest angle you can get is going to be parallel to the surface. And if you have something that would have to bend out more than that, there's nowhere for it to get in the lower refractive index medium. So in that situation, what will happen is the light, instead of getting out, is trapped inside. It will reflect back in. An example of this, if you've ever gone swimming and you end up going down below the water and then you end up looking up at the surface. One of the things that you may end up noticing if you look at an angle, so if you small angle, you'll be able to see what's going on above you. But if you end up looking over further to the angle, bigger angle this way, you'll eventually see something that would be surprising in a pool. You'll see the bottom of the pool over here. And that's because the light that would be coming in there is coming in at too steep an angle. The light can't get out. So the only place for the light to go is back down in toward you. So it's going to end up coming in that way. So that's an example of total internal reflection. To be able to calculate it, the biggest angle it can be is 90 degrees to the normal, because otherwise it doesn't get out. So we can calculate then at what angle the light ends up having to stay inside. If it's bigger than that angle, then it can't get out, so it has to bounce back in. And so then you just plug into Snell's law with an angle of 90 degrees, and you end up finding your angle of total internal reflection will be the arc sine of the ratio of your lower refractive index to the higher one. Bear in mind, the number for your high refractive index will be frequency dependent. So what will also end up happening there, if you end up looking up in that direction in a pool, but you end up looking almost at the point at the very edge of it, you'll end up seeing a rainbow there. And where that rainbow ends up coming from is because the light that gets reflected, can be refracted back to you, the angle depends on the frequency. So the one that can end up where the refractive index is the largest for red light will end up having the lowest angle, so you'll end up seeing red first. Then as you end up going over toward violet, the angle will be a little steeper. So you end up seeing that little rainbow line up there before you see the light reflected back from the bottom of the pool. And if you've never done that, but you have a chance to get out into a pool, you do that, and now that you know what you're looking for, if you do that, you'll be able to notice that you see it. That's what he ended up telling us about. So another thing that total internal reflection that you see as an effect is how gemstones are cut. If you've ever been to the Smithsonian and you end up seeing various gemstones, you'll notice that if you look at a diamond like the Hope Diamond or something, and you compare it with a ruby or with a sapphire or something like that, you'll notice that there are more facets that are cut in a diamond than you'll see cut into an emerald or something. That's not because the gem maker did a poor job. What it meant was for diamond, your angle of total internal reflection is less than it will be for other things like aluminum oxide. And so for that reason, you're trying to maximize the number of internal reflections. That's what causes the sparkle effect of a gemstone. You also get the sort of shimmer effect because whenever it comes out, if you've ever seen a backlit, you see a little beam of light come into a diamond and you see what happens on the outside, you'll notice these little rainbow effects. That's again because the angle of total internal reflection is different for different wavelengths. So it ends up separating out a little bit in that way. So that's what's happening with total internal reflection. Another important thing is looking at what happens when light ends up hitting an interface and transfers through it. And that would be if we're talking about a lens. Now, if you have light that comes in a straight line to a vertical spot, it would end up passing straight through. But notice your angle here relative to the normal, if it's coming in perpendicular to it, it's going to be a zero angle. So there's zero, because so the sine of zero is zero on this side, sine of zero is zero on that side. So it doesn't bend as it goes through. So if it's like a flat pane of glass, then the direction it comes in is at least close to the angle it comes out. If it's a thick pane of glass, it's a little different, but we won't worry, because we're thinking about things that are very thin. But if you have something that is part of a spherical mirror, then what will happen is, as you end up having light from various distances going in a straight line this way, the angle here that's normal is different. So you end up having different angles that it bends in on the other side. And I end up giving an illustration of that with a convex side lens in your notes. So in that situation, again, that the normal up here is like this. So if it's coming in this way, you'll have this as your angle, so it'll bend in, and then whenever it gets to the other side, it will bend back out, because it's going from a medium of high refractive index to a medium of low. And in general, when we're talking about a lens of the same type, if the light comes in and it's bent like this, you get a greater effect if you have the other side bent back the other way. So the effect is reduced if it's bent this way. So, and if it's flat, you end up having basically an effect on one side, not on the other. The text ends up talking about the lens maker's equations, so it goes into gory detail about how you can calculate that. I don't think it's particularly important for us. We have limited time, so we won't worry about the lens maker's equation. But just geometrically, in terms of what we're talking about with lens shapes, that's what we mean. If you notice the diagram I drew, if we have, again, light coming in a straight line coming into a convex side lens, and you have like a straight thing on the other side, if it's bent, it's even a greater effect. Then what will end up happening is the light will end up coming in and collecting at a point on the other side. So whenever you have light rays from a long distance away coming together to a single point, just like when we had mirrors before, we also end up talking about a focal length of a lens. And the focal length of the lens is how far past the lens you'd end up having to have where the light rays appear. In this case, it literally comes together at a single point. We end up calling those converging lenses, because light from a long way away converges to a point. If you have the lens bend back the other way, so it's bent back like that, then it's bent like this. So if you have the light coming in like that, backwards. So the light comes in like this, then what happens then is the light on the other side gets split out. So then if you take those light rays on the back side, you end up coming back further over here. They would appear to be converging back to a point on the side of the lens where the light came from. And that will end up being a negative focal length, and those would be called diverging lenses. All right. In terms of how we describe these, we'll end up looking same sort of thing with spherical lenses, where you've got a spherical piece on one side, a spherical piece on the other side. Excuse me. That we'll use a lot of the same notation that we did with mirrors. The big difference in terms of this, we'll still have an image height, object height, same sort of thing we had before. Those were basically unchanged. Your object distance is how far in front of the lens that the light source is. Your image distance is how far behind the lens the converging light appears to be. So if you have a negative image distance, it looks like the light, so bear in mind, if you think about a thin lens here, if the light source is over here, you'll be over here. So if you're looking through a lens, right, the light is on this side, it comes into you. So you're on the opposite side of the lens. In this situation, both of those directions are positive. How far it is here to the lens, that's your positive object distance. How far it is from the lens to where you'd have a focal point, have the light come together over here, that would end up being an image distance, so positive image distance. So the positive value for object distance, positive value for image distance are on opposite sides of the lens, whereas for a mirror, they're on the same side. So you might say, well, why do we want to end up doing this? Why don't we try to be consistent and have it on the same side? The biggest reason for that is it's nice to end up having fewer equations, right? If we do our notation that way, we can end up using exactly the same formulas we had for our mirrors. So it turns out with those definitions that we end up having my thin lens equation is the reciprocal of the object distance plus the reciprocal of the image distance equals the reciprocal of the focal length, just like it was for a mirror. So again, as long as you remember the difference in the geometry, then we end up having that. And magnification, it works the same way too. So the same formula, the same ratio. It's the magnification is the height of the object divided by the height of the image divided by the height of the object, which is also equal to the negative of your image distance over your object distance. So again, the numbers on that very, very similar. Now, the fact that it's as simple as this is because we're always assuming that the distance that travels through the lens is very small. So that's the thin lens approximation. If it's not a thin lens, then things get way more complicated, and we don't want to go there. So we're not going to end up worrying about that. We mentioned that you are not responsible for the lens maker's equation. You're also not responsible for Brewster's law. Technically, we might have been able to have enough time to do that. What Brewster's law, just really, really short, is about that if you wondered why sunglasses are made that are polarizing sunglasses, what's the purpose for that? The reason is that whenever you get light that comes in and strikes an object and partially reflects, that the light that ends up reflecting will end up, depending on the relative refractive index of the medium on this side and the medium on the other side, that can end up reflecting only the light that is polarized in this way. So if you have sunglasses that are polarized the opposite direction from the way that this would end up coming in polarized, that totally kills that, and so you end up talking about where the light ends up, sort of blinding you, where sunlight hits a reflective surface and comes in your eyes. In that situation, it kills off at least a large fraction of that, which is why you do it instead of just being dark color. Having it polarized ends up being much more efficient in stopping that type of glare.